Alright guys, so for this lecture, this is the final lecture for this weekend. I'm going to just introduce the chapter 4 material that she hasn't covered yet. And what this has to do with is we're going to be looking at just our introduction to reactions essentially. And we're going to look at enthalpy and entropy, and we're going to look at how favorable reactions are, and we're going to use a very repetitive setup of of reactions that she may include on the exam, not sure yet. And she's going to expect you to know how to show how much energy is formed, whether it's favorable or not, based on like on the delta H values. And she's going to expect you to know how to show the arrows how this reaction propagates. So I'm going to show you how to do all these things. So just this is from her notes, straight from her notes, okay? From her notes, she gives this example. So she gives this reaction. It's called halogenation of alkanes. Halogenation is just halogens halogenating an alkane. So adding a halogen to an alkane. It's what we did earlier with the isomer example, if you recall from the video. I said the monobromination of this whatever chain. Monobromination is brominating it. So it's same thing. It's just a general form of saying that. So and we'll discuss about how the isomer thing relates to this and how it all makes sense. But essentially, so she gives us this reaction. So CH4, this is our halogen, Cl2, heat or light, CH3Cl, so this is the halogenated one, and this is a side product, and this is other side products. Okay, this is our main product that we're interested in. We want this, right? The heat and light is what initiates the reaction. It allows it to occur. So this is giving energy. So either light or heat or whatever, and it's allowing us to just begin to initiate a reaction. So here we have mechanisms, and we're going to become very familiar with a mechanism. So this reaction in particular has to do with free radical halogenation, and this is how it occurs. So a radical, we've talked about negative charges, we've talked about positive charges. We now have to talk about when you have a single electron on a molecule, and this is called a radical. Okay, and a radical is formed when let's take HCl for example. It's formed when I have an even division of electrons between the two atoms. So let's say something comes here. Let's say like a lot of light, a lot of energy comes. And what it's going to do, it'll break the bond evenly between these two molecules, these two atoms. So one half gets one electron and the other half gets the other electron. And I draw these half arrows to represent one electron going to a different region. And that's how you do it. Normally we draw an arrowhead like this, and that represents both the electrons going to some area, right? So the half arrow represents a radical, which is just the word for saying one electron, and it's moving to one of these atoms, right? So in this reaction we have chlorine, right? And this is what we're interested in. We have chlorine, it's bonded to another chlorine, and what's happening in the initiation step, and we'll talk about what that means, is you have light, okay? Light is coming, and it's giving enough energy to break the bond between these two chlorines and to allow radicals to form. So when this is going to break, and I'm going to form two chlorine radicals, okay? So the product of this reaction would be 2Cl with a radical, right? And just like a negative charge and just like a positive charge, these radicals are not fully stable versions of the atom. So these atoms are going to go and they're going to come and attack other things so that they can get another atom, right? They want another electron, sorry, so they can have a full octet, or to balance this deficiency of electrons. Right, so the first initiation step is forming these chlorine radicals. Right, so we form chlorine radicals. And this is called initiation because these chlorine radicals are going to then be used in the reaction container to react with our reactant, right? So our reactant here is CH4, okay? And so what happens is I have this CH4, so I'm going to draw out 3 of the hydrogens. I'm going to not draw, I'm going to draw only 1 of the hydrogens. And I have this chlorine radical, okay? Draw it up here. And what happens is the chlorine radical is going to come and it's going to come and attack this hydrogen, right? Okay. Actually not going to attack this hydrogen. It's going to do this. So I'm going to draw the arrow right here, and I'm going to draw an arrow right there. Okay. So these half arrows converge here. Okay. And then the remaining half arrow goes onto the carbon. And what I get is this right here, right? I get the radical on the carbon now. So I have this CH3 with a radical. Okay, so this is unstable and this is going to continue. So this is why this is going to continue the reaction. This is why this step is called propagation, because it's going to, the Cl initiated it. I formed a Cl radical, chlorine radical, and now I've formed the carbon radical, and this carbon radical is going to propagate a reaction. And this is called propagation because, and we'll see why. So this CH3 radical, and all this is all together in the container, right? So I add these, then I add a lot of Cl2s together, and then I have these CH3 radicals, and now these are gonna react again with our Cl2s. So it's gonna do the same thing again, right? And what's gonna happen is I'm gonna have this half reaction over here, and then I'm gonna form another Cl radical. So what this is gonna do, I'm going to form a CH3. Now it has a Cl plus, right? Plus, and what also formed over here? I formed one of my side products over here. I formed HCl over here. I formed the acid over there, and this forms another Cl radical. And this is the most important part. This is why it's called propagation, because as long as I continue forming these Cl radicals, this is going to come again, and it's going to repeat this part A. So this is going to come back again, attack another CH4, and it's going to make more and more and more of these things. And this is going to keep happening until I run out or until I reach equilibrium, okay? And this is essentially it. And this whole reaction is going to be represented by this right here, okay? So this is the reaction. And this is the mechanism part. And what she's going to expect of you is to show the half arrows on the exam and what's happening, okay? So half arrow right there, half arrow right there, right? And then half arrow right here, half arrow right here, half arrow right there, right? And then these are our products, and this is gonna keep going back in. And I want to form this, okay? And then step 3 is termination. Okay, so there's ways for this reaction to stop, as many ways there are to propagate, right? I mean, not as many, but there are ways to propagate the reaction. There's ways to stop the reaction, and stopping the reaction is when we get rid of our radicals. So continuing the reaction is forming radicals. Stopping is using them up, right? So she shows 3 ways that this can happen, and obviously there's many of these all together present at the same time. So these essentially form side products that are not desirable. So Cl2, which is fine. This may happen if our equilibrium for CO2 Cl2. So the Cl2 equilibrium, when this becomes too low in concentration, this might occur more, right? To form more Cl2 so that it can return it back to where it was, right? And then another way this can be terminated is Cl plus CH3. So this is the one that we want. This is the one that we want, right? I want to chlorinate my CH4. And then another side product that we don't want, right? So I don't want this. I want this, right? And then I don't want another one of these. So this is a CH3 with another CH3 radical, and this is just going to form, right? CH3 bonded to a CH3. Okay, I don't want that, right? What I want is this. This is what I want most, the most desirable thing. And so that's essentially what you're going to be expected to know how to do on an exam question. Okay, and I'll show one of those. And the next thing that we need to talk about a little bit, so I'm going to go to our notes really quick. Right, so I'm taking all this from here, and let's talk about these things right here. Okay, so just gonna take a picture of this. All right, this is all hers. All right, so we have this thermodynamics. So this is what we all know from Chem 1, right? Products over reactants, and this is the represents the equilibrium constant. When the equilibrium constant is greater than 1, right, we have more products than we have reactants. So when this is the value for the equilibrium. So the value for the equilibrium is more than 1. That means our reaction is favoring the products more than the reactants. So when it's less than 1, reactants more than products. You get the point, right? And so this value just represents 1.1 times 10 to 19. This is a very positive and greater than 1 value, right? So this is obviously favoring the products, okay? So it's just what determines KEQ. And this is what I've been talking about all along, right? With acids, resonance, this is stability again. So like I always have said, and what has Rene has always said is, when we talk about which one of these molecules is the most stable, we say that's synonymous thing, which one of these molecules is lowest in energy, right? So these are the same. And then when we're looking at this, we want the energy of the products to be lower than energy reactants, right? So I went from high energy, so I had like a lot of potential, and then I used that potential and I went to a lower energy state. So I went from high to low. So that's what I prefer. I go from high to low, and as you can see with the graph she's gonna fill in, it looks like that. Okay, it's gonna look something like that. It might look more like this actually. Okay, and sometimes you can have multiple peaks and troughs, but in this case, it's very simple one. We're going from high to low, and whenever we do this, we have a net, right? This is known as an exothermic reaction. So energy is released. So the energy of the reactants is higher than the energy of the product. So to get there, energy was released. Okay, so that's what she's saying, and that's essentially it. Aside from that, so then we want to look at this delta G. So we're looking at enthalpy and entropy. And enthalpy is the heat of the reaction, heat evolved or absorbed in a reaction, right? Result of a bond changes that occur. So where is energy coming from? Energy is coming from when we break a bond. So we have atom A and then atom B, and we break this bond, energy is released, right? So this is where energy is coming from. And energy needs to be, we need to give in energy so that we can break the bonds. But the bond sometimes releases more energy than we put in, and that's what gives rise to the exothermic reaction, right? We form products that are more stable than so the bonds that we broke and the bonds that we formed are in difference of energy. So the bonds that we break gave off more energy than we needed to use to form new bonds, and that's essentially what we did in the reaction, right? We broke the bond between Cl2 and between the CH and between the carbon and the hydrogen, right? We had that CH3 and the hydrogen, and I had the Cl2, and I broke those bonds, and I formed these new bonds. These new bonds are lower, they required less energy to make than these gave off. Okay, that's the gist of it. So what's important, the takeaway for this is to understand how to calculate. She's not going to make you do like endergonic, exergonic, and delta G values and stuff, but what she's going to make you do is she's going to make you calculate the delta H values. So she's going to make you calculate the bond dissociation energy. And so essentially what that is she's going to give you a table that has the bond dissociation energy values of many different types of bonds, and she's going to make you calculate it given what you have. So the way that's done, so delta H is equal to the energy. Actually, I should be typing this up. Okay, I'm going to type it up. So energy of the bonds of the reactants minus energy of the bonds of the products. Right? And this is what I've been saying. So right? So this is what I've been saying. So delta, right? And so we're looking at how much energy is in those bonds between the reactants that we break, and then how much energy is in the bonds that we're forming. So if what I'm forming um, is going to be lower energy than what I'm breaking, then I'm going to have a favorable reaction. Okay, and usually what this means is if my delta H comes out as less than 1, then I have a favorable reaction. Okay, if my delta H naught is greater than 1, then I have a unfavorable reaction. Okay, so it comes off as negative, then it's going to favor the products. So from reactants to products, if it's negative, it's favoring the products. If it's positive, it's favoring the reactants. Right? So that means we're looking at when the energy of the bonds, the products. I know it makes not as much sense, but when this value is higher than this one, then we're favoring the products. Okay, and when the value of this one is higher than this one, then we favor the reactants. Okay, and it makes sense because if it's saying the energy, I guess that's given off, I believe, to break it. So if we give off more energy breaking these, then these would technically break. Then we would have a non-favorable reaction. I mean, we would have a favorable reaction. Okay, so don't get confused in the details, right? Let's just do a practice problem to demonstrate. Okay, so I'm going to take one of these from the exams, right? And we're going to just look at it really quick. Give me a second. I don't have one. All right, here we go. So this is what I have. So this is what she says. She says, an equation representing the halogenation of an alkane is shown below. Provide the propagation steps of the mechanism that explain the formation of the products. So we have, she's given us this, given us Br2, light, and then we form this and this. So she says, provide the propagation steps. So we don't need to show initiation, right? She wants to see propagation. So she wants to see what's happening. So let's take a picture of this. All right. And this. Okay. So I need to show how this happens. Right? So we know in the initiation step, light came and broke this, and I had half reaction. And I got Br radicals. Okay? And this Br radical, so step 1 of this reaction, okay? Br radical is here. I have a hydrogen, right? I form HBr, so that's a hint. So I have a half reaction here, and I have one of these electrons here, and I have an electron going there, okay? So this is going to form the radical on the ring right here, plus HBr, and then B, we're going to have this guy, right? And then we're going to get Br2, right? Because that's where we originated our Br radicals from. This is the propagation step. So I'm going to have a half reaction here. And I'm going to brominate. Br plus a Br radical is formed. And this allows it to go back again and again and again. All right, so this is what she wanted to see. Okay. Now, the next step says consider the termination steps. Provide a structure for a possible side product. And so what did she say, right? What did I show you guys? So possible side products is termination, right? So either you have the Cl2, which is already given, is already there, and then we have the product that we want, and then we have the radical of the molecule reacting with itself, right? So we have this guy, we either have Br reacting with a Br radical, or we have our molecule reacting with what we want it to do, or we have, right? Or we have our molecule reacting with a Br radical, not the Br2. Or the bad one, another bad one that we don't want is our molecule reacting with itself. So I have these two radicals, and then I have a half reaction, and it gives me this. Okay, I drew that bad, but they're the two rings, okay? And this is what you would draw, okay? You would draw this. And this is what she wants to see, right? So she wants to see, in this box, she wants to see this structure right here, okay? That's what she wants. All right, and now the last step is given the bond dissociation energies below, calculate the overall delta H for the reaction in the box provided. You must show your work to receive credit, okay? So what she means, just show like your calculation, okay? So I'm gonna copy this. All right, and I'm gonna go back and I need to write the equation. So I had this thing, right? I'm gonna draw a hydrogen here, Cy, plus Br2. HV is just another way of saying light. And what I get this. Plus HBr, okay? So I'm actually going to draw this out more. All right, so this is all I need. This is all I need. So what I do is delta H naught equals, so first I need to find the values, right? I need to find the values of the bond between carbon and hydrogen when carbon is connected to two other carbons. So two other carbons, right? Just a quick side step, right? When carbon is attached to two other carbons, right? Right, this is called a secondary carbon. When carbon is attached to only one other carbon, this is called a primary carbon. When carbon is attached to three carbons, this is called a tertiary carbon. And you can even have quaternary if there's all carbons around it, but we're not really interested in those because you can't really do anything with that. So we're interested in primary, secondary, tertiary carbons, and that just refers to how many other carbons a carbon is attached to. So we're looking at this carbon right here, and you'll see why I'm bringing this up because it's part of the table. It's attached to this carbon and this carbon. Okay, so it's attached to two other carbons, so this is a secondary carbon. Okay, so I have a secondary carbon that's bonded to a hydrogen. This is the bond right here that's broken. I have a bromine bonded to a bromine. I have a secondary carbon, right? It's the same type of carbon bonded to a bromine. And then I have a hydrogen bonded to a bromine. Okay? So these are the four types of bonds that I'm interested in finding the values for, right? She'll give you all the values for these. So let's look. So this is the table that she gives us. So let's read it. HX bonds and XX bonds. X represents halogens. So we have HH, DD, FF, whatever. So Br2 bond is 46. Okay? So this is 46. All right? And we also need to find bonds to secondary carbons, right? So that's what we have. We have a secondary carbon, the H, so it's 95. Okay, so this is a energy value of 95 here. Okay, and then we have a secondary bond to a bromine, so this is what we're looking at, 68. Right, and then HX, so HBr is where? HBr is right here, 88. Okay. All right, so all we have to do is just, it's going to be, right, it's over here. So it's going to be the energy of the products, the bonds of the, the bonds of the reactants. So 95 plus 46 minus 68 plus 88, right? And then we have to calculate this, and I don't feel like calculating this in my head. You will have to though, because no calculators are given on the exam. So 95 plus 46, so this is 141. Okay, and then we have 68 plus 88. Oops. So this is 156. So I already know this is going to favor, this is a negative number, so 141 minus 156, right? So not that hard, but I'm doing it anyways with a calculator. I hate math right now. So negative 15. And you have to make sure you show the value. So it's kilojoules, right? It's in terms of kilojoules. Oops. What is the value? It's in, let's see. Yeah, it's not kilojoules, it's kilocals, my bad. Right? So kilocals per mole. You have to write that. And then are there products or reactants favored in equilibrium? So because it's negative, products. All right, and that's it. Okay, so that's basically it for all of this chapter 4 stuff that will probably be on the exam. And we'll just be going over stuff on Monday. Now, for those of you who've watched all my videos this far, so for those of you that watch this far, I want you to, there's going to be a quiz on Monday, and at the end of the quiz, I'm going to ask a question about the shape that I draw here. So the shape that I draw here is me attempting to draw the boat shape for the chair conformation intermediate. So if you guys remember this, right? If you watch all the videos, this will just let me know that you're actually watching. All right, see you Monday.